Okay, let's start. It's my utmost pleasure to have James Riely giving a talk at this research colloquium. James has made my task very simple. I just have to read one line of his bio. But none of us need any introduction to James. James has taught at DePaul since 1999. And the talk that he's giving on, he's been working on 10 years. And if I understand what James is going to be presenting is his most recent OOTA paper. Is that right, James?
That is correct.
Yes, and just to give the students over here a little bit of context, OOTA is the topmost conference in programming languages. Not that James needs another feather in his cap, but what we are going to learn is the state of art in memory models. So on to James to help us understand what memory models and relaxed memory models are about.
Thank you, Tanu. So see if I can get all my technology to work here. I have a screen down here with you guys in Zoom, and I'll pull up the chat window. If you have questions, though, it'd probably be best if you speak up, because I doubt I'll be able to pay attention to everything at the same time. I've done a really good job as a researcher here, and I've been very dedicated to the research. And as a result, well, we'll see how this talk goes. Okay, so the reason I'm doing this talk now is that the conference is in about a month and a half. And so I'm doing this as sort of a way of practicing what I want to present, and also a way of forcing myself to sort of get it coherent. So the nice thing about this idea, in fact, I encourage you to do this. Normally, I'm not this disciplined. And so what happens is I'll submit a paper, and then after the paper is in and it's already being published, I'm like rushing toward the end of everything to get slides together and to have. Then the thing that happens is whenever you actually try to present your work to someone else in an intelligible way, you find that you can actually say it better than you said it before. And so what's nice here is that this gives me an opportunity to talk to you guys about this work before the final camera-ready copy for this paper is due. So just last night, I actually made a major simplification to this paper at 3 a.m. when I woke up. So I spent most of the morning messing around with that. So if the talk gets a little chaotic toward the end, well, so be it. So this is joint work with, let me, sorry, get up. I need, yeah, there we go. Let's see if this is going to work for me. Yay, okay, I've got a laser here. So this is joint work with Radha Jagadisan at DePaul and Alan Jeffrey at Mozilla. He's just left there and he's now joining something called the Servo Project. And let me see how I can move. That's not working. There we go. A little bit slow there. There we go. All right. Everything's looking good. All right, so the basic question I want to start with is this one. All right, can this program write one? And actually, can somebody tell me, can this, so I'm assuming that, you know, here R is a register. So I'm reading into R here from Y. So this thread is reading the variable Y into a register, then writing the value that it just read out to X. This guy's reading X and copying it into Y. And of course, over here, we just have this irrelevant write into Z. Now, if everything is initially 0, can this program write 1? Is it possible for 1 to show up here? Anybody?
Not from just that program, but I guess it could be written by
someone. Yeah, no, this is just a sanity check, right? Okay, there is no way this program can write anything but 0. Okay, so this is just baseline sanity. And the term of art that's used for values like 1 in a program like this, it's called a value out of thin air. Because there's nothing in this program that has anything to do with the value 1. So it would be absurd if this program were to write 1. And in fact, if programs like this were allowed to write 1, all sorts of safety guarantees that we expect about programs would be out the door. In particular, you know, in languages like Java, we assume that pointers can't be forged. You can't just make up a pointer to an object in a secure location and start messing around with it. That's not okay. You're not allowed to just invent values. You have to be given them. And so this is a very, very fundamental thing that we expect about semantics. Okay, so essentially this whole talk is going to be about examples like this one. So the first thing I want to look at is that, you know, as Jordan pointed out, in certain contexts, something like this might actually be able to write 1. So let's look at a context where what I'm going to do is put this thing inside of a conditional. So we're just going to take the thread on the right and put it inside this conditional, which is that if I read 1 here for from Y, well, then I'll do this copying business like I did before. And I'll just put an else branch here, which is that if I didn't read 1, or excuse me, if I didn't read 1, if I read 0, well, then I could write X is 1 over here. Now this is, you know, by everyone's intuitions, you should say, well, that program should still not write 1, okay? Because it might write 1 for X, okay? But if it wrote 1 for X, then it didn't execute this branch over here. And therefore, we'd never expect to get 1 for Z in particular. You know, Z here is going to be 0. If Z is written at all, it's going to be 0. That's what you would expect. Is everybody with me? Right, we're going to do one side or the other. If you do the else branch, sure, you get X is 1. You might even then get Y is 1, but you're certainly never going to get Z is 1. You're good with that? All right. Well, it turns out in relaxed models where we have compiler optimization, a program like this can actually write Z as 1. And so let me just walk through how that happens. The first thing that a compiler might do is it might notice that X and Y here are globally only either 0 or 1. Therefore, it can take that line that says, you know, Z gets R and change that into Z gets 1. And likewise for X gets R, that can be turned into X gets 1. And as a result, we can bring those things out because now we have X is 1 on each side of the condition. We can take it outside of the conditional. That's just lifting common code. And at this point, we can then commute these independent statements because what I've got here is a read of Y and a write of X. And there's no, you know, necessary dependency between those. So commuting them makes perfect sense. These are all perfectly valid optimizations in a single-threaded world, okay? What happens here, though, is that in the concurrent world, we've got the possibility of concurrent observer, and the concurrent observer can read the value I just wrote and then write it back to me. If we interleave this concurrent observer in between the write of X now and the rest of the thread, well, you can see then very obviously this can possibly write Z is 1 because what do? Well, I just execute it, you know, left to right at this point. So we're going to read 1 into Y. We're then going to do the execution of the conditional and we'll write Z as 1. Any questions about this example? So note that if we change this to 2, if all I do is change the unexecuted code to 2, then this actually becomes possible, the same execution, you know, replacing 2 everywhere for 1. But if I have a 2 up there, one thing that'll never happen is that I'll actually get a 1 out at the end. Okay, so is this a good thing or a bad thing? This is my question. So if it's these kind of examples can be sad for people. You might feel, somewhat conflicted about this. I just told you that this was sort of reasonable step by step as the compiler goes through that, and every little step sounds reasonable. But when you go back to that program, it really doesn't seem like this thing should be writing 1. Okay, so how do you go about understanding a program like this? I guess this is what I'm trying to ask. Obviously, one thing you could do is you could actually look at how the compilers actually works, right? So if you understand everything about compilers, well, then you can reason, oh, well, this thing might write 1. But trying to think about the concrete implementation of a programming language, it's not something everybody wants to do. So, and in fact, compilers may vary. So one compiler may do one thing, another compiler may do something else. And usually what we do is we try to define a language standard, which is actually what we use to check the correctness of a compiler. So if we don't have a understanding of this apart from compiler optimizations, then what does it mean for compiler optimization to be okay? How do we check that our compiler is not doing crazy things? Okay, and that's why this kind of thing has been sad. It creates a lot of anxiety and conflict in the world, and in fact, for at least 15 years, people have been looking for a solution to problems like this that will allow the executions we want, but it won't allow executions that we don't want. And this turns out to be much trickier than anyone would have ever thought. Okay, so what I'm going to do is make your life wonderful. I'm going to give you a soothing balm of calmness and security. And I'm going to give you it using all formal mathematical definitions, nothing left out. I can define everything you need to know about this kind of program in 4 slides. Okay, so I'm going to do it. By the way, I'm going to run through these definitions rather quickly. I want to give you a feel for how complex this model is. I want to give you a feel for the size of the definitions that you need to do to understand, to actually work through these kinds of models. The thing we're going to start with is the idea of a partial order. A partial order is hopefully familiar to you guys. This is a order which is simply acyclic. Just think of it as an acyclic order. We don't have any cycles. We've got some set of events, and we've got some labeling. So this is a labeled partial order, or a Pomset. And my Pomsets labels are going to have a little bit of structure. So I'm going to have 2 things in them. So I'll have formula, those are logical formula, and actions. All right, so in addition to the labeling function, I'll give myself these 2 accessor functions. And since I've got these preconditions, I'm going to put a little bit of sanity between the preconditions and the order. I'm going to require just 2 things. One is that all of the preconditions within the Pomset have to be mutually compatible. Okay, so if I take the conjunction of all of them, I should get a satisfiable formula. And the other thing I'm going to require is that the order and the formula sort of play nice together. All right. Given that, I'm going to give you 2 more definitions. So one is that we'll have write actions and read actions. And so a write action is going to fulfill a read action if 2 things hold. So one is that the write action must precede the read action in order. And the second one is that any other write action on the same variable must either be ordered before the write or after the read. That's all. Okay, so this is the notion of fulfillment. And now I can say that a Pomset is sort of closed if it satisfies 2 properties. And we'll do these per variable. So I'll say a Pomset is X closed for some variable X if, first of all, every read of X is fulfilled. So you need to fulfill all the reads. We have to have a write to match every read that we're reading. And the second thing is all the formulas need to be independent of X. So in other words, in order to close over X, we need to be sort of done with X, right? So we've fulfilled all the reads, we've satisfied all the formulas that involve X. With these, we can define some operators. So the first one is this operator, which just takes a set of Pomsets, that's script P, and takes a subset of them. So this will be, this new X denotes the subset of P that is X closed. There's another operator here, which is a filter. So this is a filter which is going to filter down P to be only those Pomsets where every single precondition in the Pomset implies phi, right? So that's a filter operation. We have substitution. So if we have a set of Pomsets, well, we can just go through and do substitutions in the formulas of those Pomsets. So note that I'm never actually going to do any substitution in the actions, but in the formula, we'll do some substitutions. So then we have a sort of complex definition here. And what this is doing is parallel composition. So more or less, parallel composition is union. So if I have two different Pomsets, I can union them together. So you can see here, I'm taking the union of the edges. And of course, I want the union of the order as well. In order to compute the labels, I'm going to do something a little bit funny, which is that either the label is coming from the left-hand side, or the label is coming from the right-hand side, or it comes from both of them. So this gives me the possibility of coalescing two events from both sides. And when I coalesce events, the formulas will be ordered with disjunction. So I can do a disjunction this way. So if something is either from the left or from the right, if I can get it either way, then I will just be able to get it with the disjunction of them. So that's the only complication there. This definition is the last one I'm going to show you of these operators, and it's a complicated one. But what this is doing is prefixing an action. So I have a new action at some formula that I'm going to prefix in front of a set of Pomsets. And let me just zero in on a little bit of this stuff. Most of this stuff is just sanity checks. It's saying, you don't do anything bad. So let me just look at a few bullets here. So the thing is, we're going to add a new event a new event D to this Pomset. And note that just like we had with parallel composition, I'm not doing disjoint union here. So it may be that D actually occurs in E. So we may actually be coalescing this with something that already exists. But for the most part, you can just assume that we're not doing that in this talk. And now there's just a few things I need to look at. If D is a read or if it's not a read, we'll have slightly different behavior. And what this is doing is computing the formula for that thing. All right, so rather than belabor and look through these definitions, I'll revisit these with examples in a second, all right? So given these operations, this is the semantics of the language. That's the whole thing, all right? So we have the ability to terminate. So this is a skip action. We have read and write. Excuse me, this is a register initialization. This is a read. This is a write. This is an if then else. We have parallel composition, and we have variable declaration. And we're using all of the operators that we define. So here we're using substitution, we're using prefixing, we're using the filtering operation, we're using parallel composition, and we're using new, right? So the restriction operator. We're going to throw one more thing in here just since it's easy. Each of our actions will actually have an annotation, and the annotation will tell us the access mode for that operation. So it'll be a relaxed, release acquire, or sequentially consistent. So if you've never seen memory models before, these things might be a little bit unfamiliar to you. I'll show you some examples later. All right, so that's it. That is everything you need to know about memory models in 4 slides, all right? Now, you might say, that seemed like a lot of math. So I am not doing a huge survey of related work here, but suffice it to say that that is a shockingly small amount of math for anything in this area, okay? So let me show you what we can do with it. And I'll just start off looking at the example we just saw. Okay, so let's go back. And for those of you that are interested, I'm going to write down the two most relevant rules down here. And so what this is telling you is this is the rule for prefixing a read and the rule for prefixing a write. And these are the rules for calculating the preconditions as we go. Okay, so that's the most important stuff from those definitions. I won't be referring back to the definitions, but you can look at them if you want. So here is the semantics of this program. So Z gets R. What does it mean to say Z gets R? Well, okay, well, one thing is I could write, Z is 0. And I can do that as long as R is 0, right? So that makes sense. The precondition here is recording the dependency on R. And of course, I could write something else. I could write 1. Yeah, I could write 2. And what we'll get is one Pomset for each possible value that we could write. And you can see that down here in the union. So we have a union over all possible values. Okay, now if we do 2 writes, well, we'll get 2 events in our Pomset. So in this case, you can see I've got the write of X and the write of Z. And of course, the values could vary over time. I could write 1, I could write 0. One thing that is tricky, though, is, if you look at these definitions, the computation here is independent. So this is something that needs to be considered. I might write one value for X and a different value for Z. And what happens in this case is that the preconditions become, if you take the conjunction, now I have R as 1 and R as 2. And of course, that is unsatisfiable. So that'll preclude this kind of Pomset from being considered. So what that means is that I have to have the reads reading the same value. Okay, let's look at this now on the left-hand side and this separate program on the right. So here, note that the precondition in this case is trivial because what I'm calculating here is that the thing that I'm assigning is equal to the value I've chosen. Here I'm assigning a constant, and therefore the precondition is trivial. I'm going to keep it around, though, just for so you can sort of see how these things are calculated. Okay, and now let's put these things inside of some control flow. So on the left-hand side, I'll have if R. On the right-hand side, if not R. And you can see that that's going to add in a little bit of an extra dependency here. So note now, in addition to just having 1 is 1, I also need to know that R is 0 in order to hit that else branch. And over here, I need to know that R is not 0. Okay? Given that, then, we can now put these, let's simplify them a little bit. And then we'll put them together. So I'm going to join these guys in the rule for if. And what the rule for if is going to allow me to do is to coalesce using that parallel composition operator. I can coalesce the 2 writes on the 2 sides and weaken the precondition using disjunction. Okay, so note that Z just sort of pops down, but the precondition for X now is either we read 1 or 0. Given that, well, note that we can't, in the case that we had X is 2, we wouldn't have been able to do this. So just pointing this out. So note that if X is over 2 over here, I don't have any equal labels on the left and the right. There's nothing that can coalesce, and this dependency would be carried through. And by the way, this is the essential difference between writing 2 up here and writing 1, is whether or not I can coalesce this write of 1 with the write of 1 on the other side. All right. So anyway, this would not be allowed as well. By the way, note that in this case, right, I can't actually have all 3 of these actions together because they would be disallowed. Okay. All right, in any case, let's start fresh from here. We'll back up. So this is the program we've got so far. Is everybody okay with this so far? That makes sense? Yeah? Well, I'll take, yeah,
Can you
Jordan.
just define what exactly a Pomset is?
Oh, Pomset, yeah, a Pomset is a partial order with labels, that's all. Okay, so note that there's no order here. So you might be like, oh, these are just events with labels. That's all they are. Is that helpful? Okay, cool. All right, so given this then, let's keep going forward. Let's see what happens. So what I'm going to do now is prefix a read of y in front of this guy. Okay, and in order to do this, what I'm going to do is we're going to do this in 2 steps. And again, if you look down at the semantics of read, what it does is it does a substitution of the variable for the register. Okay, so x for r. So in this case, I'm reading y into r. So I'm going to substitute y for r. And so again, going back, we had here, we'll go to this step. Okay, so I just substituted y for r everywhere. And now what I can do is actually add the action. So after the substitution, I will add the action in. And so here the read action shows up. So there it is, yay, a read action. So when I put that read action in, I'm actually forced to do a few things though. So if you look in the rules for prepending an event, there's some obligations you get for read actions, okay? And in particular, if you read v for x, then you must obey this restriction over here, all right? And in this case, what does this mean? It means that, well, in addition to knowing that y is 1 and y is 0, in this case, I also need to know that 1 is 1 or 1 is 0. Okay, so what I'm doing is choosing the value that I've read and substituting it through in this formula. And so I did the same thing over here. So we had y is 1, and of course when I substitute 1 for y, I get this. So now I have this additional constraint, 1 is 1 or 1 is 1 or 1 is 0. Okay, so that's then going to also prevent us from doing bad things. So note that if I read 2 here, well, I'd end up with this precondition, which is 2 is 1 or 2 is 0. And note that this is not satisfiable. Okay, so this whole thing would be disallowed in that case. So I've got to be reading something compatible with what I've got. When I've got a compatible read, I have this option of introducing order, and that's here on the last line, P5A. There's this possibility of introducing order between the new event and some old event. And when I do that, I can weaken the precondition of this. So note that I either need to preserve the precondition or introduce order. When I introduce the order, I can actually perform a further substitution here and actually go ahead and substitute v through for x. So what that's going to do is actually get rid of y altogether. Now we're perfectly happy, and that guy is satisfied. Okay. I'm going to do one more thing here now, which is to prepend a right. So prepending a right of y. Note that that has a trivial precondition. And what does a right do? Well, one thing it does is it actually does a substitution. So we'll substitute the value that we're writing, in this case 0, in for the variable that we're writing to. And what that's going to do is cause everywhere in our world here, wherever we have a y that still is not resolved, that's still free, we'll go ahead and substitute through. And what's interesting here is that we get different values for y depending upon when we did the substitution. So note that this guy, when we did the read of y, we could substitute for y with 1. When I prepend this right, I can substitute with 0. And it's this thing of, this is essentially what's going on in this kind of program, which is that the different occurrences of y here can be satisfied in different ways. All right, so in other words, it's like you're reading y twice. Okay, so there you can see we've got some order from the read. note that the right, if we have a local right, that doesn't put any dependency in here. Okay. Simplifying all of this, you end up with just this guy right here. That's it. So that's how you can calculate the sequential semantics of this program. Once you've got the sequential semantics, the concurrent semantics is relatively easy, okay? So the first thing I'll do is I'm gonna add a new little rule here, which is to say if things are conflicting, as I prepend them, I've got to introduce a little bit of order. And so I'm using a different color arrow here just to indicate the cause of the order. So here, when I've got the write before the read, I need to introduce an order between them because they're on the same variable. Let me also introduce an initializer for x, and likewise that x must precede anything that's before it or after it. Okay, and now we can take the parallel component, which was going to copy x into y, and we'll just stick that here. So you can see there's the parallel component copying x into y. So we have the initialization, the parallel component, and then our program that we've been studying so far. Yay. This all looks great. We just need to do one more thing, which is to satisfy the fulfillment requirements. So the fulfillment requirements say that every read must have a prior write that gives me the correct value. Okay, so in this case, that's going to tell me I need to have the read x of 1 preceded by write x1, and the read y1 preceded by write y1. Okay. With all of this in place, we're done. We have completed all of the requirements, and this tells us that this execution is allowed. All right. Why? Because it's a partial order, it's fulfilled all the reads, and all the preconditions are tautologies. Okay, so nothing is dependent on any variable. Any questions about this? So again, this is the same example we saw at the intro, walking through with compiler transformations. Here it is, and what we're doing is really just tracking dependencies, yeah? So we're just looking at global dependency order here. Okay. Note that if we make a small change, if we just change x to 2 here, then this dependency is now enforced. So now, if you remember, when I change this to 2, I cannot just generate a write to x is 1 here without actually reading y is 1. There's no compiler transformation that's ever going to give me this write of 1 for free, and therefore I must see it. And now when I do this, I get a cycle in the causal order, and that tells me why this is disallowed. All right, great. So what I'm going to do is just take the initializers out because they kind of clutter the picture. And let's just go to this simple picture now. So here is the allowed execution where I've gotten rid of the initializers. And note that in this case, there's no dependency from the read to the write of x. All we're saying here is that this, another way you can think about it is in horologic. If you looked at this thread on the right, it can always produce a write of x is 1, regardless of what y is. It will always be able to write x is 1, right? And that's why this independency is here. There's no dependency between these guys. Let's do another small change.
Quick question about that.
Yeah.
So the position of the squares there, so we're writing, like, is that sequential order? Like first you're reading x is 1, then writing y is 1, and then, so writing x is 1 happens after you're reading y is 1? Is that what that?
Yeah, so the time order is, it has to obey the causal order here, okay? So, I mean, if you wanted to unravel this thing, the first thing that would happen is write of x is 1.
Okay, gotcha.
Yep.
All right.
Any other questions? All right, so let's just make a small change here. And And what I'm going to do is swap the condition. So note here, my condition is on R. And this is very important in this example because it's if R is not 0, then I will write R. Okay, since 0 and 1 are the only values here, I can assume that if R is not 0, then it is 1. And that's why I can write 1 here. This changes rather dramatically if we flip that condition. Instead of being conditioned on R, let's have it conditioned on some arbitrary coin I flip. Okay. If I do it, note that in this case, the write of X is 1 now is again dependent on the read of Y. So note that this dependency gets introduced based on whether or not the write of X actually requires the read to see the same value. And in this case, it does. And therefore, we end up with this dependency, right? This is obviously disallowed. Yes, because of the cycle. Everybody sees the cycle? All right. So not okay. All right. We can actually prove that this execution is impossible. In fact, I can prove that it's impossible to write Z as 1 here. And it uses temporal logic. So what this says is that if you write Z as 1, then at some point in the past, you must have read that Y is 1. And at every moment of the past before that, if we had read X is 1, then we must have at some point in the past before that read Y is 1. And further, we know that if we have ever read Y is 1 in the past, then we must have written X is 1 in the past. All right, so this is the invariant you can use to show that this thing it's impossible, and there's a logic in the paper to actually allow you to prove this. So with sound proof rules.
And
what's weird about this example, though, is that so many attempts at solving this problem get this example wrong, and I'm one of them. So in 2010, proposed a speculative semantics that actually got this wrong. So it was wrong in Java. It was wrong when I tried to explain Java in 2010. And it was wrong when some other people followed the same idea in 2017. This, by the way, is probably the leading candidate for replacing the Java memory model in a future version of Java. And I think this shows that it's really not okay. There are other kinds of semantics that get this right. And I did one of those in 2016, but it's worth pointing out that these models are all too strong, okay? So what that means is they don't allow enough executions, and this means they can't be efficiently implemented on hardware. So this is where you're kind of between a rock and a hard place when you come to memory models. If you make the model too strong, it's inefficient. If you make the model too weak, you get this spurious nonsense behaviors. And these spurious nonsense behaviors aren't just bad in some sort of like, oh, I don't understand why it's there bad. You can argue that we don't understand why any of this stuff is there. It's all bad, right? So, but this is really bad because it breaks temporal reasoning about safety properties. There's a very similar example in a paper from 2013. Yeah, Ben?
So,
did you have a question?
Yes, I did. So on your previous slide, I saw that you cited ARM. Did you also research it on ARM, or did you look at other CPU types as well?
So, I'm talking about the formal specification of the ARM version 8 memory model.
Okay. Okay.
Yeah. Yeah, it's approved by ARM itself. So ARM actually publishes a formal model of their memory model.
Yep. Okay.
Yeah. Okay. Great. All right. So this example is from 2013 by this Andrew Slockbuehler, and he wrote this paper studying the Java memory model. And what he showed is that the Java memory model has an execution of this program where everything in the program is typed as a D object. So I type Y, X, R, Y, R, X, R. All of those are of type D. note that there's this other register over here, S, assigned to a new C, but this is in a branch, you know, presumably not executed, or that doesn't matter. But actually under the Java memory model, it turns out that this program has a legal execution where X is actually assigned a C object. And as scary, that makes no sense. I just want to point out, right? So, but it turns out to be an artifact of the Java memory model. And it's because of what happens here is that the S object is sort of in exactly the same way we can sort of commute things out. If you think about allocation and then assigning types as two separate operations, what happens here is that the allocation can sort of slip out. The object can then be slipped from Y into X and come back around and come through here. And then we can read our own allocated thing before we actually even assign its type. This caused Lochbihler to notice that type safety fails for Java, and therefore he partitioned memory by type in order to get a theorem to go through. And what that means, though, is that you have separate parts of the heap for every single type in your program. Like there's a little subheap for Ds and a little subheap for Cs. And this is absolute nonsense when it comes to realistic memory allocation. So there's no way to pre-allocate your heaps, one heap per type. So it really doesn't make any sense from an implementation point of view. And even worse than that, Lochbihler showed that this kind of example, even with type safety, invalidates a lot of the security guarantees of Java. So in particular, if you have security sensitive constants, they can actually leak out through this kind of code. All right, so this is a major problem, and our paper is the first one to solve this. So that's the major contribution here. Any questions at this point? Yeah.
So when you say that cycles are not allowed, is that specifically the compiler optimization where we're making all these changes, that's when it becomes invalid, or does the program itself just have undefined behavior, like the original program?
Sorry, say it one more time.
So on the previous slide,
Yeah.
So you show that there's a cycle there, and so
yes,
that cycle is an artifact because we were doing compiler optimizations, right?
So no, the way to think about it is that in this model, right, you're forced into this cycle by the constraints, okay? The constraints have the dependency. In order to satisfy fulfillment, you would need to have these read from edges in here. So obviously we have to get, read one into X from somewhere. And likewise, this read of Y has to be fulfilled somewhere. And these are the only writes that could fulfill them. And then because of the dependencies, this becomes a cycle, and it's therefore disallowed in the model.
Gotcha.
Okay? So that's the way to think about it. This is an invalid execution. Does that answer your question?
Yes, it does.
So the thing is, if you think about validity in terms of what compiler transformations you can do, you're really putting the cart before the horse, okay? Because compiler transformations, the compiler could do all sorts of nonsense that might be terrible, okay? You can't just say, well, this is okay because the compiler does it, if you know what I mean, okay? You want to have some sort of standard. I know I introduced all this stuff by showing you what compilers do, but actually all of the things that I showed you there are also done by hardware. Okay, so ARM 8 will do all those reorderings that I talked about as well. Okay, all right, so that's the kind of problem you end up with. This is the major contribution of the paper, and so if I stopped right here, I would be happy. Okay, so what I'm going to do is just give you a sense of the rest of the results in this paper before we go away. And I'm not going to necessarily explain all of these examples, but I'm just going to walk through a few common litmus tests. This is a buffering litmus test. So if you know the Intel architecture, you can have a program where you write x is 0, y is 0. Then you have a thread that writes x is 1 and then reads y. You have another thread that writes y is 1 and then reads x. And it's possible for both of these reads to see 0, okay? And the reason is that there's no dependency between the write of x and the read of y, or between the write of y and the read of x. And that's reflected in our model. Likewise, you may know that many architectures allow what's called load buffering. So when we have load buffering, what that means is that this example is possible. So I can read y and then write x as 1, and then in a separate thread, read x and write y as 1. And again, because of the lack of dependencies between these, it's possible for these to see each other's reads. Right? This is stuff that actually happens in hardware, and therefore it's important to support it in a model. There's other things that happen. Okay, so this is 4 examples of what's called an internal read. So this is where in hardware models, the reads from your own thread are treated differently from reads from other threads. And they don't introduce the same dependencies. So when you have a foreign read or an external read, that is always guaranteed to be in your dependency relation, whereas an internal read is not. All right. Our model just handles all of these kinds of examples correctly. That's all I'll say. These are things that are very challenging for other models. And this is an execution, for example, that invalidated one model. It's allowed under ARM. And there you go. Adding synchronization in this model is not difficult. You just need to add a few constraints. So in particular, if you look at the first constraint, we just say, well, if the new event I'm adding, D, is an acquire, and the old event is a release, well, or excuse me, the old event is a release, then I need to order them. And there's some similar things here for other things like sequentially consistent reads and writes and fences. Anyway, if you do this kind of stuff, you get the correct result. So let me just walk through the most simple example. So here I'll write x is 0, then write x is 1. And then I will write into a variable y using release acquire semantics. So this is a releasing write. In the other thread, I'll do an acquiring read. So here I've got order across. And after that acquiring read, I'll then read x. So the meaning of release acquire here is if you have a releasing write, then it's going to order everything before it. And that's why I put this blue arrow in. And the meaning of a acquiring read, it will be ordered with respect to everything after it. And that's why I get this blue arrow here. And because of this, this execution is actually invalid. So this is not allowed. Why is that? It's not allowed because it doesn't satisfy the fulfillment requirement. What I'm doing here is I'm seeing a stale value for x. And in particular, the value that I'm seeing here is old. And the second requirement of fulfillment said that any other write, like this write x1, either must precede the write or follow the read. And this doesn't do either of those things. And therefore, this is disallowed. There's a lot more examples of publication that we could go through. There's also this thing called sequentially consistent memory. And I'm not going to belabor what it is. There's also something called fences. Fences are complicated. They just work out here. And there's a lot of compiler transformations you might want. And almost all of them are going to work in this model. Okay? Let's just pick an example here. This one. If something, then do something, otherwise do the same thing. This looks so innocuous, right? If im, then c, else c. That should be the same as c, right? This fails in almost every memory model. Okay, so this, as far as I know, this is we're the first model that satisfies this. So there's a bunch of other things that you might want that are perfectly sensible. These are about reordering. So if you have two writes that are independent, you can reorder them. You have a read and a write, you can reorder them. You have two reads, you can reorder them. Sometimes you can order with respect to release acquire or other things. And there's other sorts of things one might do. This is another thing that's actually tricky in most models, which is that if I have a parallel composition of some program and another program and a scoping of a variable. So this is what's called scope extrusion. So the scope of X is expanding out to include C. Again, this is false in almost every memory model. All right. Things that you would expect to be true. We do have to do a little bit more work to get these transformations to be satisfied. This is general read elimination. So is it sound to eliminate a read? Well, you have to be careful about that. Is it sound to eliminate a write? Again, you need to be a little careful about that. Write elimination is something that requires a bit of work. You can look at the paper. And likewise, read introduction. So you can introduce reads, but only under certain circumstances with a slightly more abstract view. There's stuff that's invalid as well. And I don't have examples of these things, but thread inlining, that's where you take two different threads and put them together sequentially. That's not valid in most of these memory models. And you can see the reason. When you have sequential things, you actually get more possible executions from those sequential things, because certain things that were external before are now internal. And therefore you can get more executions by inlining, so it's not sound. Likewise, introducing a relevant read. So if you read something twice, it's actually, you might see different values instead of reading it once. Introducing writes is never sound in a model like this. And redundant write after read elimination is also unsound. So these are some unsound things. Other results that are in the paper, this compiles efficiently to ARM. And it also has this property called local data race freedom. So what local data race freedom means is that you can think about a program sequentially as long as it doesn't have races, okay? So the actual way the theorem plays out is it says, if you've got an execution that has a race, then that race is present in some sequential execution, sequentially consistent execution. So in order to do this, you need this drag around this concept called program order. That's the order things appear in the program. And what you need to do is look for cycles in program order and causal order, like this kind of cycle here. And if you've got this kind of cycle, well, that means you better have a race. And in fact, here we do. And what we can do is break that race by moving over here. So note that what I'm doing is just changing the read. So I'm going to read something different. So rather than seeing the stale read, I'll see the better, newer read. Okay. But there's a race here. This execution is sequential, but I've got a race. One more example like that. In addition to seeing stale reads, I could see future reads. So if I'm seeing a read from the future here, I can, this is not, there's no way to do this sequentially. So I need to break this cycle in order to get a sequential behavior. And the way I do this is simply by looking at an older read. Okay, so again, readjusting this and I get an old read. And that'll give you what's called data race freedom. So again, data race freedom, what it's saying is that you get sequential behaviors for data race free programs. Okay, so that's the big picture. We've been guided by some principles here, and the principles make us happy. And the main principles we've got here is that there's one order. So we have a Pomset, and the Pomset has those nice arrows. Humans are really good at looking at one order and sort of finding cycles in it and things like that. We're really bad if there's more than one relation. Thinking about two relations can be extremely difficult, even trivial ones that are related. So having one order is extremely important here. It does mean that we compile really efficiently to ARM v8, which also has one order, or Intel, which has one order, but we will not compile efficiently to like Power or ARM v7, which have essentially require multiple orders. Another thing that's very important is compositionality. So our semantics is compositional. It's probably only the second semantics of a weak memory model to be compositional. And what that means is that you can calculate the meaning of a program from the meanings of its subprograms. Right? This is extremely important. We also allow compositional reasoning about safety as a result. So you can reason about programs in isolation. And logic is the key that keeps all of this going together. So the way we've been able to use this, we've actually used logic in two ways. So one is that we use it for the preconditions in order to calculate dependencies carefully. And we also use it in proving this compositionality property. If you looked at, remember the example, I had a temporal logic formula in there. And so these temporal properties, we're reasoning about the temporal properties of these systems and doing it in a compositional way. And that's it.
James, I have a question.
Yes.
So you know, this Pomsets sort of relies on, is it my understanding correct, that you have to propagate these labels across the various statements? And I'm wondering, like, if you know, in normal execution, sort of in provenance tracking, if we are propagating labels, that has a significant overhead. I'm just wondering, in compilers, this label propagation, does it have an overhead?
Oh, that's interesting. Well, of course, this is a purely theoretical model, right? So there's no overhead in the implementation sense, right? So what is the purpose of a model like this? The purpose of a model like this is to serve as the intermediary between programmers and implementers. So if you're implementing the language, the model constrains you, you know, in terms of how much freedom you have to reorder things, because the model may say, oh, you can't reorder those things. And if you're a programmer instead, the model is your friend when it says you cannot reorder things, right? So these things are guaranteed to be in this order. So yay, thank you, and it makes it simpler. So the more order makes it simpler for programmers, and, you know, if you like, harder for implementers to get efficient code to run.
Right. Right.
But the order itself is purely a formal device, right? So it's not actually carried around at runtime. Sure.
This model is for static analysis, if I understand. I'm wondering, like, whether the model can be useful for when you actually do a runtime execution of this program. Is there something additional that you might infer that, well, you know, these orders that you identified, I mean, there was a lot of inferencing that was required to be able to identify a given order, but, you know, if you know some partial execution of the program itself, then yeah, maybe your model gets simplified, or the number of paths sort of it has to determine, or the number of rules it has to go through to determine what particular orders exist.
That's interesting. Yeah, I mean, there may be some application like that, but I haven't thought about it, right? So
sure.
Yeah, I mean, in some ways that's because we're defining what it means to be a valid execution at all, right? You can't use the execution and to justify anything here, because this is that would be some sort of circular reasoning, I guess.
Okay, I got to go actually for my meeting, but I'll let others ask. Yes, thanks.
Okay, all right, thanks.
I have my hand raised for a couple questions.
Okay.
See you, Tanner. The first is very simple. Why is your model shorter than previous models in terms of mathematics?
Why?
You mentioned that it's much shorter, it's better, it's stronger. No, it's not stronger, and depending on the sense, but
stronger is not necessarily good here. Yeah. So the reason the model is better or shorter, there's two reasons. One is, and they're related. One is that we're using a single order. That is a major simplification. So without the single order, things are much more complex. Okay, and we're able to get away with using one order on ARM and TSO only because we're doing extremely precise dependency tracking using preconditions. Okay, so those are the two things that make this model work and make it precise and simple. Okay, the great thing about it is that you know, this idea of using Pomsets to model the semantics of programming languages goes back to the early 90s. And the idea of using preconditions to reason about program goes back to the 60s. So all we're doing here is mashing up the 60s and 90s in order to solve a problem for the 2020s. So the moral we took away is don't throw away your old ideas, just try and reuse them.
I like that. I like that.
Yeah. In fairness to everyone else that's been working on this problem for 20 years, this one order thing is something that only was enabled recently because ARM changed their memory model. Okay, ARM had a much more complex memory model which would not support the use of a single order up until about 3 years ago. And 3 years ago, they realized none of their manufacturers were actually using that freedom, and it was making life miserable for programmers and compiler implementers to understand what the hell was going on. And so they simplified the model to use a single order, and that's what allows us to do this and still compile efficiently to the two most common platforms on Earth, which are Intel and ARM.
Fascinating.
Also RISC, by the way, RISC has adopted this platform. So.
And a completely unrelated question. You mentioned a few times topics related to memory consistency. So is there an application of some sort of your model to memory consistency in different levels of cache?
Yes, absolutely, absolutely. So that's what this is modeling, actually. So in fact, if you think about the buffering examples, yeah, the buffering examples, this is precisely modeling cache. Okay, so what you've got here, in fact, the top one, the store buffering example, this is a standard TSO example or Intel example. So I write X is 0, write Y is 0 into main memory. Then I write into my buffer, my cache, X is 1, but then I read Y out of main memory. And this guy is just doing the same symmetrically on the other side, okay? And so this is exactly a cache, it's modeling a cache effect.
So can these be...
So all of these relaxed models, essentially what they're providing you is an abstract understanding of caches. That's exactly what they're doing.
That's very cool. Can this provide new approaches to memory consistency on the fly rather than, you know, Snoopy caches or any kind of?
No, I don't think so. This is I mean, that's an interesting idea, but yeah, we're way up in la la land of math. I have no idea that this actually could be useful. Yeah. So yeah, no, I doubt that this would give you any sort of insight into how to efficiently do a cache. Having said that, our previous work sort of on this topic was related to Spectre attacks. So in Spectre, and in modeling that, you essentially drop the consistency requirement. So if you remember right at the very beginning here, when I introduced Pomsets, I said that we expect that the, there we go. Yeah, that one. We expect consistency. So all of the formulas must somehow be this, you know, satisfiable. In order to model something like Spectre, you actually drop that requirement. So you allow incompatible worlds. Yeah. Because exactly what Spectre is doing is it's seeing the false branch of the conditional. And the false branch of the conditional has an observable cache effect. All right. And so that's actually how this work started, was trying to understand Spectre. Cool. So this is a sort of second time around this with this particular idea, and this time we're trying to model. So when we're modeling Spectre, we're modeling microarchitecture, because microarchitecture you actually can see the cache effects. Whereas here we're doing an architectural model where those are invisible, and therefore you have this kind of satisfiability constraint. Right, so we're not looking at incompatible worlds here. Yeah.
Thank you.
Yeah. Thank you for the question. Anybody else?
Yep, I have another question. So you mentioned that Java might be getting a new memory model. What exactly would that mean for the language? Like, would they
So for most people, it won't mean very much. It's meaningful to compiler implementers and people that are doing low-level, high-performance concurrency primitives. So if you're implementing a concurrent library, then it would be relevant to you. Okay. So the history here is the Java 1.1 or 1.0 was one of the first languages to really define what concurrent access of memory meant. That was in 95. And then in around 99, it was discovered that that model that was proposed in the original Java language specification disallowed a lot of compiler transformations. And so for about 6 years, there was a big project to come up with a new Java memory model, which was published in 2005. But that model actually has the problems that Lochbihler noticed and that I presented here, okay, which is that it does allow some sort of thin air behaviors, which you wouldn't expect. There's sort of, the reason actually is because Java, what it does, the way it works is the Java memory model is you can think of it this way. It tracks, it allows you to speculate on the future. So you can speculate that eventually you'll write something, and you can read that speculation early. You have to justify the speculation though. So if you like, every time you speculate, you sort of fork two branches of your execution. So in one branch of the execution, you can see the speculated value, and in the other branch, you can't. And now in both of those branches, you're forced to produce the value that you speculated on. So that's sort of to stop the thin air stuff. But the reason that doesn't work very well is you've only got sort of one tester, and that if the tester has any way to get to produce that value, then it's considered okay. So, and if you think, I don't know if I can get through the slide to that slide easily. I'm using Firefox as my code viewer, and it's the slide viewer, and it's not that great. Anyway, if you think about this little switch here from, there we go, from there to there. All right, so in the Java model, it's possible to get this weird execution because there is a way. So what you do is you speculate that you'll write X is 1. Then you immediately read it over in the left-hand thread, copy it into Y. Then you read the value you speculated over here. And now, of course, you can proceed. And now you can produce the speculated value. You can produce this write X is 1, right? So, and the side that the justifier here can't see the speculated value, but of course what it can do is just read a different value from B, and then it'll write 1. So it's got a justification, if you like, for what it did. And that's what Java does. That's what all these models do, right? So they're doing this kind of speculative execution. And it seems very fragile. So it's enough to prevent some thin air things, so that one checker is enough to prevent some things, but it's not enough to prevent everything, and in particular this one. So when you have a universal quantifier, you say no matter how you execute, you need to produce the value. That's a much stronger requirement, and it'll prevent things like this from happening. So, but the problem is that if you require every possible future to get there, you end up being too strong. Okay, so having one is not enough. Having everyone is maybe too much, and that's where we are. So somewhere in the middle. Anything else? Questions?
Is there a, oh, Ben, do you have a question?
I was gonna ask, have you looked at I know you talked about ARM and Intel. Have you looked at any other processor memory models like the good old days like ZOS?
I had a hard time understanding.
Oh,
Sorry.
I know you keep talking about ARM, but have
Yes.
you looked at other processors?
Oh,
like
yes. Thank you for that.
Yeah.
Yeah. So the model works for TSO, that's Intel, and any Spark-based model. So that includes PSO and RSO or RMO. Oh no, not RMO. Sorry, that one it won't do. RMO is too liberal, but nobody ever implemented RMO anyway, so it's fine. The ones that are implemented in hardware that we know that this one satisfied are Power, the Power PC model, and yeah, so ARM v7 actually it allows things that we don't allow, but in fact, there's no implementation of ARM v7 that uses that. So the only one that I know actually in silicon that would disallow this is the Power PC. Yeah.
On the same topic, I wonder if IBM did the same thing on the mainframe side.
Well, they've done it for RISC, so I don't know about the other stuff, but they've done it for RISC. RISC v5 is adopted the same thing as ARM.
Oh, yeah, and are there some languages that have, like, can the constructs of the programming language itself produce a simple or more complicated memory model? In particular, I'm asking about, like, are functional languages easier to model their memory usage?
No, this is definitely underneath all of that, right? So what we're looking at the grunge under the hood. So this is the stuff like the compiler targets. And so we're not at source level here.
Gotcha.
So none of that would be relevant, there are languages with memory models that are trying to do this, and essentially it's all the safe languages. So Rust, Java, JavaScript have memory models like this. C++ has an interesting, or C and C++ have an interesting model because they do define things on atomic access in C and C++. But if you have races on regular variables, you get undefined behavior there. So they walk an interesting line trying to give you definable behavior for relaxed access. It's been very tricky in that world. Anything else?
All right, thank you very much.
All right. Well, thanks, guys. If you have any suggestions about the talk, please message me. So I know there's some few errors in the slides there. Sorry, Michael, what?
Missing a parenthesis on slide 27. That's the only
Missing parenthesis on slide 27. Okay. All right, cool.
Have a good one. Cheers.
All right, ciao. Thank you. All right, bye-bye, guys.
Bye.
Have a good one.
All right, you too.